Okay, let's start with the afternoon session to be on time. So, hello, good afternoon. I hope you have enjoyed the short break and the lunch, and we will continue with the lectures. And let me introduce Professor Ondřej Caha, who is also working at the Department of Condensed Matter Physics at the Faculty of Science and Masaryk University. So, like Professor Humlíček started, I suppose Professor Caha will continue. So, happy to have you here, and the floor is yours.
Thank you for your introduction. So I will talk more about structural properties and defects in wide bandgap semiconductors, and we'll try to explain why they are so important. Yeah, it's results of our long-term collaboration with mostly onsemi. And we also collaborate for some time on gallium nitride. So I will now on silicon carbide, so I will also show some results of gallium nitride architecture on silicon. So I will start with some introduction, crystal structure of wide bandgap semiconductors, silicon carbide, gallium nitride, and so on. Also briefly mention gallium oxide, but unfortunately have any experiences with gallium oxide. Some defects and methods for analyzing analysis of defects in semiconductors with a focus on techniques by X-ray scattering and X-ray diffraction. So first of all, I will show some simple structure like gallium nitride, which is Wurtzite lattice structure, when there is hexagonal planes. It's like stacking in a grid. If you have hexagonal planes, then there are three possibilities how these hexagonal planes could be stacked on each other. So if we look at gallium nitride, we have gallium plane and nitrogen plane with the same stacking, and then there is another bilayer of gallium and nitrogen in the second plane. And so on, and it continues just repeating these two stackings. That is one of the consequences of such structure is that if we have a surface which is 0,0,1, like this hexagonal plane, then it always breaks in this position between gallium and nitrogen, because there is much lower number of bonds which we need to break up. Then we cannot never break here, and there is 3 bonds. Here there are only 1 bond per this unit lattice. So the consequence is that we have one side of a crystal or the layer which is terminated by gallium, and the other side is terminated by nitrogen. And that the surface is always polar, so we have surface charge which we cannot avoid by any cost. We cannot cleave it, we etch it, whatever. Still, this termination is all the time present. So the gallium nitride is relatively simple. Silicon carbide is much more rich in crystal structures. So we have a simple Wurtzite structure, and there is silicon and carbon planes, AP stacking, and so on. We have cubic stacking, and there is 4H stacking when there is stacking like AB, AC, and so. So we can look at the literature how it's with these stackings. So in principle, of each bilayer, we can define whether this bilayer is in hexagonal or is it cubic environment. So the next both neighboring bilayers are different, and it's kind of cubic stacking. If the neighbors of, for example, this B bilayer are both A, and it's hexagonal stacking. So there is some old Jagodzinski notation when one can simply state it's just hexagonal stacking all the time. Then it's a 2H structure. If there are only cubic stackings, it's called 3C because the period is 3 bilayers. If this is 4H, then we can see that it's just hexagonal and cubic stacking periodically in a periodic environment. So as well, so it's the ABCB, and then the period is 4 bilayers. If it's 6H, then 1 hexagonal and 2 cubic bilayers, and so on. So then the layers, then the period is 6. And if we have something like a combination of 4H and 6H element, then we got 50R. Then the period when it goes back to the same ABC, AC is 15 bilayers. So in literature, if you look, there are something like 30 polytypes because it can continue to never ending. One can construct simply infinite number of polytypes. So we can define an hexagonality, which is the number of bilayers is in hexagonal or bilayers in cubic environment. So from that we can simply define a hexagonality of each film. And I took from this picture from some or similar. But if you look at the gap and gap dependence of the hexagonality, we find this dependence of hexagonal. The band gap is much bigger, something like 3.3 electron volts at low temperature, and then cubic is something like 2.4. And depending on the hexagonality, the band gap is growing with higher hexagonality, the bigger the band gap. So 4H polytype has actually quite high hexagonality, 50%. So the band gap is quite large. It doesn't get bigger if we go to 2H polytype. So from the size of the band gap of the common polytypes to 4H is the biggest, except of those. And these are some planes which we can look at the silicon carbide. So most often we can have we work with a 001 plane, which is the basal plane of the hexagonal lattice, and also as similar as in the gallium nitride, we have one phase which is silicon terminated, another phase which is carbon terminated. And yeah, it means that because nominally silicon and carbon should be charged, should not be ionic, but slightly they are ionic, so it's slightly for the surface. So it's not absolute zero, but the surface of the 001 is slightly more. For the other wide bandgap semiconductors like gallium oxide, so it's much more complicated. And I just look at the literature. The gallium oxide has at least 5 polytypes, of which I just show 3 of them. And for the semiconductor industry, this beta type gallium oxide is the one which is actually supposed to be, can be used in a semiconductor technology. Advantage of gallium oxide is that it actually could be in principle grown from half. It's not like gallium nitride or silicon carbide. So if you look at these tables about the mobility and breakdown fields, so for from silicon carbide polytypes, the 4H polytype has the highest mobility in comparison to 6H and 3H, and also very high breakdown fields. So it's for high voltage devices the most best polytype from the silicon carbide polytype. So, I will show some defect characterization. So this is just a rough table how what type of defects we can have in semiconductors or generally in any crystals. So we can have point defects, vacancies, interstitials, anti-side defects, like atom occupying the position of the other one. For example, if carbon is incorporated in a silicon side and so on, or impurities, I will not talk about them because they cannot be detected by X-ray related methods, and usually those defects are not so affecting the electric properties so much. The most important are dislocations and some inclusions and voids or inclusions of other crystalline polytype in a crystal. Just made some, I didn't know how advanced this is a publicum here, so I just made some slide introduction. What is a dislocation in a crystal? So if we, for example, put some additional atomic plane just ending somewhere, we can we make a defect in a crystal structure, which can be described by so-called Burgers vector, which is something if we make some circle around and there is some additional or missing part of the crystal lattice, then there's the Burgers vector. And if you have a plane incorporated in a crystal additional and there is a missing or it's a missing plane from the bottom, depends how you look at it, then we have so-called dislocation line where the dislocation is, and the Burgers vector, which in edge dislocations it's perpendicular, and we have screw dislocations when it's Burgers vector is along the dislocation line. So dislocations, if we have a epitaxial film on a heteroepitaxial film on a substrate which has different lattice parameter, that we cannot grow film with infinite thickness, which would be laterally lattice matched to the substrate. So because then the strain energy would be too high. So in principle, we then the layer after some certain critical thickness gets relaxed, and we just put a crystal which has bigger lattice parameter on a crystal which has small lattice parameter, or vice versa. Yeah, there are misfit dislocations which are forthcoming interface. We cannot avoid that. It's growth with a different lattice parameter of substrate and film, and according to properties of dislocation, dislocation end up only on the surface, or could end up at some other dislocation, but cannot just end somewhere. It's not possible. So if there are misfit dislocations, then there are also so-called threading dislocations going through the film, the surface, and the goal is actually to get as small number of threading dislocations as possible. By Alice also how to grow stacks of the films to decrease. So this is I just calculated the number of dislocations per line. It's not per square centimeter, it's per line. So that's relatively low. So, but if we get a number of dislocations in a that it will be just something like square of that. So it's, so if we grow gallium nitride silicon, then the resulting concentration of dislocation something like 10 to the 10. Just I mean, for the misfit dislocation, it's concentration of dislocations in a plane, so it's per line. It's inversely linear. So then the question is the threading dislocation, because misfit dislocation has to be there, and if they are very long, then you have very low number of threading. So what kind of dislocations are in gallium nitride? So there are several dislocations, screw dislocations, edge dislocations, and kind of mixed type of dislocations when there is a dislocation with Kruger's vector, which is not perpendicular nor in line of the dislocation. And also some other defects. For two-dimensional defects, the most common defects are stacking faults, which incline in a crystal, or additional plane in a crystal, or some missing plane. I just want to know that every stacking fault is at the boundary of the stacking fault there is a dislocation. So dislocation is surrounding the stacking fault. So some defects in silicon crystal, silicon carbide layer. There are some. Look from the top. There are so-called micropipes and closed core screw dislocations and some growth speeds, and in very unfortunate case, some triangular occlusions of other polytypes, which is in terms of taking fault of something. I think this is how it looks on a microscope. So, and there are defects which are then usually in literature described as a carrot type of defects or shallow. So, from that, there are some typical densities of dislocations, which are usually hundreds or thousands per square centimeter in a silicon carbide bulk crystals. One of the biggest concepts are so-called micropipe, which is dislocation with Kruger's vector bigger than lattice parameter. So actually, how I would show it. So it's if we have some atomic plane, so it's very distorted with the step height is bigger than one lattice parameter, and this resulting strain field in the center, close to the center of the dislocation, is so high that it's energetically preferable that there is a hole inside. So it's so there is a free space in the middle of the dislocation. So it's energetically preferable to form some hole or tunnel, and so and then there are some other dislocations, and from the effect of the effects on the electrical properties, one can say that most of these threading dislocations in Schottky diode or MOSFET are supposed to have a very low effect in some more complicated structure with a pure junction. These defects, this dislocation probably reduce the lifetime of the carrier charge carriers for the more bigger defects, these micropipes and so on. It can cause micropipes can even kill the device at all, and for the other defects, at least they reduce the breakdown voltage. So they present some shortcut in the device, and they reduce the possibility to operate in high voltages. This is some little bit similar table with the micropipes that can cause breakdown bigger than increase breakdown by more than 50%. So methods of the analysis of the structure. So I will talk most about X-ray diffraction, but also some other methods I will briefly mention is like emission microscopy or electron microscopy for imaging films, and then I will show some results of epitaxial films of gallium nitride on silicon with determination of strain and dislocation density on this, and some results from bulk silicon carbide crystals. briefly, I will just mention some methods which we did not use, but just to make some completeness. Emission microscopy in principle is that the device is connected in a microscope to the electrical control unit, and the current or voltage is put there, and when there is a defect, then in the vicinity of the defect, there becomes a hotspot, literally hot part of the sample, hot part of the device, which emits light, so one can then collect the emitted lights when that is hot and find the parts when the sample and the device is leaking or when there is a breakdown electrical. The transmission electron microscope, one can also see dislocations in a semiconductor. But the disadvantage of electron microscopy is that one can see very small area, which you can you have to look at the small part of the sample, just a couple of micrometers. For the X-ray diffraction, I will start with the design of the experiment. So we have some X-ray tube, some crystal, a monochromator, which we then have a monochromatic X-ray beam impinging on the sample with the changing angle of incidence, and then some part where we detect this X-ray radiation. So we have interference or diffraction on the crystal and lattice, and we have a wave diffracting on the different atomic planes, and we get the products of the process. The equation for the angle and incident, we have a diffraction maxima from the We can have also mapping of the so-called mapping of the reciprocal space. And if we describe the incoming wave by a wave vector and the scattered wave by a wave vector, then difference of those wave vectors is as a scattering vector, and changing the angle of incidence and angle of exit, we can have a map of the reciprocal space and in the reciprocal space we see peaks which correspond to the inverse of the Fourier transform of the crystal lattice. So from that one can determine lattice parameters and all directions, and from the shape of the peaks also quality of the crystals. So some notes about mapping of the reciprocal lattice in gallium nitride, and if we have looked at the aluminum gallium nitride as an alloy, then we have to assume that in this alloy lattice parameter in plane and out of plane depends on the Vegard's law, depending on concentration, and then we have to use formulas for elastic free surface. Skip this. So we have a sample. This was some testing sample from onsemi a long time ago. So we have silicon substrate and aluminum nitride nucleation layer. Those were some aluminum gallium nitride layer, just a single layer with some certain concentration. If we do a reciprocal space map, we see a peak of aluminum nitride and of aluminum gallium nitride, and from that we can determine lattice parameters in plane and out of plane of both layers. So we can determine concentration, we can determine strain of the layer. Also, we can have a look at the width of the, and if it's a perfect crystal, there would be very sharp peak. But unfortunately, because of high density of dislocation in this material, we have a very spreading peak because locally there is some distribution of this parameter. Okay, so this is some different sample from also long time ago. We look at some little bit more complex structure of aluminum gallium nitride on aluminum nitride. So can determine the lattice parameter. So there is the gallium nitride layer, aluminum nitride layer, and some three aluminum gallium nitrides in layers between. And there is also, it's better seen in the reciprocal spacement. So one here, one can see the this position here is inversely proportional to the lattice parameter in plane. This is inversely proportional to the lattice parameter out of plane. So this is aluminum nitride layer. The red line corresponds to unstrained material. So this aluminum nitride layer is actually laterally tensile. So this is then there are three aluminum gallium nitride layers and gallium nitride layer, and on top of the surface there is aluminum gallium nitride layer for hand, which one can see it's as in plane lattice match to the gallium. So, and then looking at that, one can determine the concentration of aluminum strain of each particular layer. So some of the layers are laterally compressed, some of them are tensile. So together it's then less. So the goal was that the total stress would be almost zero, and the whole film would not almost sample. And okay, for the width of the peak, we can determine density of dislocations. There is quite a simple formula, very old, 1957, but still it doesn't mean that it's not true. It holds still up to now, more or less, at some under some assumptions. So if you look at this, although I looked in the literature, found some paper comparing the density of dislocations determined by X-ray diffraction and by transmission electron microscopy. So this looks like very good fit, but then one has to look to the scale, so some points are 4 times below, 4 times high. So this line actually corresponds to the ratio of the densities 1 to 4. Okay. One can get from that really idea of order of magnitude of the rotation concentration. You look at some a single film on top of silicon and aluminum nitride, the density of rotation is something like 4 times 10 to the 9 per square centimeter, and gallium nitride is about half. So density of dislocation was reduced because some of these dislocations just match together, and there are less dislocations than in the aluminum. If you look also at the scattering in the farther range, in the closer range, then in the dependence of the intensity on the simply scattering angle, we can look at some limiting properties and when the intensity depends on the set or force power, we can somehow extract the information about screw and edge dislocation. You look at the sample with some with these 5 layers, so we can see that the aluminum layer was this blue one, and this red one is the gallium nitride layer. So higher we got in the structure, the dislocation concentration. So there are some numbers, dislocation density. So starting from aluminum nitride, something like 4 times 10 to the minus 10 to 9 per square centimeter, got reduced about the order of magnitude. And then I will go to the silicon carbide crystal. So in the beginning, I said there are plenty of polytypes. So this is some very unfortunate sample.
This was on purpose.
On purpose, but okay. I would say it's a testing sample which include several big parts. And one very nice thing about this sample is that you can see by your eye that there are three colors, different colors of the wafer. So there is something which is blue, something which is reddish, and some part which is somewhat green. So we did mapping of this sample by X-ray diffraction. So because the different lattice period stacking differs in X-ray diffraction pattern. So we can say where which polytype is it, which part. So I rotated it so it would be more or less the same orientation. So this blue one is 6H polytype, this red one is 4H polytype, and this greenish like color is a 15R polytype. And so one can see really that these inclusions detected here by X-ray diffraction correspond really to the colors of the sample. That's what one can. Then there is some large reciprocal space map to show how it's around the certain part. So we have seen this, we can see some period corresponding in case for each polytype for different polytypes space this periodicity of this diffraction point. So it's actually very easy to differentiate. So here's how some pure polytype wafer looks like in transmission. So I think it was mentioned before that there is certain part of the crystal of the wafer which is darker, it's dark. So in the wafer one can see some this wafer. I will not say when it comes from, but this dark spot is in the center. So when the crystal is grown, then because the growth front is not flat, so it's bent. So only at a certain part of the growth plot, the orientation is exactly 0001. So this facet, there is a different growth process and also different incorporation of dopants. So we can see that there is, it actually is that the crystals is grown in is nitrogen in the atmosphere, and so high incorporation of nitrogen is at this growth facet. So and that's why, because there is higher concentration of dopants, this part becomes darker. Discussed before, so although we can have a look at that by X-ray diffraction. So I will, in the last part of my talk, show some results of X-ray topography, which is a little bit different technique than scattering, looking at the angle of the scattered radiation. But on the other side, we will radiate the sample with some monochromatic equilimated beam, and we'll look at the spatial distribution of the diffracted density. So actually here the detector is put very close to the sample. Sometimes it could be even a photographic film and so on. And what we can see, we have a very good, almost perfect crystal. That at some point we see a contrast where there are defects on the crystal. So this is some theoretical part of explanation what are types of contrast If there is defect, then one can expect that the diffraction peak gets shifted or widened, and that way the intensity could be somehow taken into account. This is, for example, in a very asymmetric diffraction with angle of incidence 48 degrees and angle of exit is about 60 degrees. We have made a photography at each of these angles, and these are some nice results of some bad samples. I would say this is a silicon carbide crystal with some ingrown inclusions of which are slightly disoriented. All the crystals 4H polytype, but there are some inclusions which are slightly disoriented. So, for example, at this low angle, we see that the diffraction condition is satisfied mostly at this part of the crystal, which is then not diffracting at high angle of incidence. This part, which is here, there is inclusion, which is disoriented on the others. On the other direction. So it's actually diffracting when the angle of incidence is higher, when the rest of the crystal is not diffracting, and you can see. So also there is other effect over here. So for the scale, this is 30 to 40 millimeters. So it's very large. So relatively large area mapping. Also, one can see some effects propagating from these inclusions. So also we use, instead of kind of photography, we can use a detector and can do more than 5 images. So we did a couple of 100 images, something like 200, and then we can evaluate the peak position as a function of the position of the sample, or the local curvature and so on. So we can see clearly these two inclusions that are the same inclusions as I shown before, and from that we can determine how much these parts are disoriented by each angle. So that's possible. For this detector, we have a resolution 100 micrometers is the size, so it's relatively low resolution to resolve small defects like dislocation, and resolve quite large. I will skip this and I will come back. So for this wide bandgap semiconductors have some advantages and disadvantages. One of these advantages is that because they have a wide bandgap, they are transmissive for a visible light. So one can look at them in visible light. So this is the same sample as before, and this is image in the polarized light. So there is a polarized light, and there is a polarized analyzer which are crossed with respect to each other. And because the silicon crystal itself has anisotropic refraction of index of refraction, and also because if there are some defects, then there is addition of anisotropy of index of refraction, which can be seen as which can deviate the polarized light. So we can see very clearly these defects in a polarized light. So here you see this is this dark spot which was in the center. I think it's all these images in the center, but this is not from onsemi. It's from some other company. If you look at the image in the polarized light and compare with the image in X-ray diffraction, we can really correspond one-to-one each part. But these inclusions are also very well seen in the polarized light. Okay. So I have just found some years ago that this polarized light imaging could be taken in the smaller dimensions that one can look at the microscopy level at some certain tuning. So, for example, the lights should be more or less coordinated, and also there we see almost individual dislocations. The crystal, this is comparison with the topographic image, but this is taken in a synchrotron. It's not a lab image. Okay, so this I will go back here. Sorry for the order of the slides. So I told so far that single dislocations have not been resolved, but they can be captured. So one of the methods which could be used is a lung type section X-ray topography, when it uses a very narrow beam and then goes through the crystal, for example, transmission. So one can then look at the diffracted image. So we see there is a defect, and it has some image on the. We see a defect on the detector as some type of contrast. Either it's increasing or decreasing the intensity. And here the detector was actually photographic film high resolution, because we don't have any good defect at all. So one can see here even a depth profile from through the wafer. So there are two lines of the wafer, the surfaces of the wafer, and there is a very very high concentration of dislocations, and there is a lower concentration of dislocations at the other side. I think this is part of some testing sample, and one part was used as a source, source for growth of the other part of this interfaces between the grown and the original sample. Yeah, we have some old machine which still could be used for this technique. I got to the end. So for wide bandgap semiconductors, still there is a huge concentration of defects. For silicon nowadays, one does not have to take into account that's because they are in wide bandgap semiconductors, either silicon carbide or any more gallium nitride or epitaxial layers. It's still some point of development like silicon over 50 years ago. So we can have now very large area to do research. Thank you.
Okay. Thanks a lot for the presentation. And do we have any questions related to defects? Another very important things. Semiconductors. Okay.
I have a question to the X-ray topography.
Yes.
You mentioned, if I understood correctly, you can depict the this one or the slides before.
Yeah, for example.
Yeah. So these pictures show the distortion of the crystal lattice or misorientation
Yes.
of the crystal. Is there any interference with the surface topography of the sample, or? I think that
yes
this sample was polished wafer, so
that's all polished wafer.
Yeah.
This was actually crystal, but there were some inclusions inside. So I intentionally chose this one because this image looks very nice.
Yeah, but if the surface is not straight, there is a
Yes, yeah, I mean, if now just try to look at the different, some samples at the certain levels of polishing and so on, and the use of those topography methods. And yes, there is also consequence, but we see also that there are some scratches, some scratch marks of, or one can look not only on the peak position of the peak, also peak width correlates with the surface. There are two things, also with the morphology and also in the subsurface. So yes, it could be used, and we are still a little bit working on how to reasonably quantify and correlate this one, yes, but it's sensitive to the surface damage, to the surface quality.
Okay, I saw.
Yeah, I kind of another question.
Ah, okay.
It was already asked.
So any other question? Okay.
So I have a question about the polytype thing. When you show this picture, you said that the red is the 4H, green is are 6H, and the yellow
Is here, this color.
it's
The
mixed.
coding is here. When it's yellow, then there is mixed.
Yeah, mixed. Oh,
Yeah, I've seen it because this X-ray diffraction has certain penetration depth, so probably there are some surface and a little bit below the surface could be a little bit different, or I don't know how it looks in the depth. So if I see here is yellow, then I have detected both points. So it's like RGB map. So I use RGB coding.
Okay. Look. Okay.
okay, question to this picture. I'd like to ask, how long did it take to scan? If you scan like the whole wafer?
It's been a couple of years, but I think it was done like overnight.
Okay.
Well, it's fast for
Commercial use.
Several hours.
Yeah, I mean, there were several like 12 or 16 maybe.
Okay.
Not just a couple of hours, it was really overnight.
Well,
And I remember maybe over that. I have to look back how I did it.
Well, yeah, it's quite similar. Like we have the top chip simulation. It usually takes also 1 to 3 days. No problem.
I mean, we know the polytypes, and then I chose the colors for the RGB coding for the polytypes intentionally, so that the colors are the same as the visible.
Okay.
Of course.
Okay. Any other questions? No. So thank you once again. Thank you. Lehce napřed a tím pádem aspoň budeme mít čas ten nachystat. Takže to jsou ty fundamentals, že? Ještě to musíme nasdílet. Ještě mám moment. Takhle si to zanalizujeme, ale vůbec. Opak, takhle. Tak zkuste si, jestli vám to bude cvakat. Funguje, výborně. Okay, we are approximately 10 minutes ahead, but I suppose not the problem. So let's skip the, let's say, academic part of the workshop, and now we will have two lectures given by the representatives of industry, and who else than onsemi. So I'm very happy we have Tomáš Novák over here. and he will give us some remarks on silicon carbide epitaxy. So,
thank you for introduction, and also thank you and all the organizers for holding this event here in Brno. I'm glad that onsemi has been mentioned a couple of times and by previous lecturers. We had a long-term cooperation with many of them, with Professor Humlíček, Professor Caha, and also other people who are present here from the University of Technology as well. In the past, we were doing gallium nitride. We are not doing it anymore, unfortunately, but that's how it is in the industry. The market wasn't there for the power semiconductor applications. On the other hand, for silicon carbide, it is very dynamically growing, evolving. So a couple of years ago, company decided that silicon carbide will be our point of focus in terms of power semiconductors and high power switching applications. So my lecture today is focused on silicon carbide epitaxy, its fundamentals. And the second part will be more focused on the technology for mass production. So equipment that we use for the mass production, how we control the processes, and what challenges we face, and what has been the recent evolution in the 6 epi. I'm glad that you've already seen this graph a couple of times today. I won't need to explain this and spend a lot of time here. The main message is always to compare the physics properties of the wide bandgap semiconductors with silicon and point out that its properties enable us to make power devices that are far more efficient compared to silicon, that can extend to higher operating voltages, powers, higher operating frequencies in terms of, for example, gallium nitride. And that's, of course, not very easy to replace the silicon. It's not replaced for every application, but in many cases, despite devices from GaN and silicon carbide are more expensive, they are so much more efficient that it's in the end suitable to use them instead of silicon devices. So here is again, a similar graph you've seen before. There is some competition area between gallium nitride and silicon carbide, but it's not large. You can also see that you can produce majority of devices also with the silicon, but again, you can produce them, but they have much lower efficiency because with the silicon carbide or gallium nitride, you can make devices smaller, you can make devices with low resistance, so they can work much more efficiently. For example, if we look at some applications such as inverters or drivers for electric vehicles, if you look at inverters for solar systems, data centers, UPS, traction, everything has much higher efficiency and therefore low losses. Now imagine what our electricity grid looks like. We generate electricity, and before it's consumed, it's converted many times. 3, 4, 5, 6 times it's converted. Sometimes, many times between alternating and direct current. And if we increase efficiency of single step by 1 or 2%, if instead of 96, we have 98% efficiency, and we multiply this 3, 4, 5 times, then we gain really huge number in what we don't lose, the energy that we generate and don't lose before we consume it. So that's why it's important to improve even by 1 or 2% for individual devices, because when we multiply, it will save a lot of energy. So in onsemi, in terms of silicon carbide, we do everything in-house. So it's called vertical integration. We buy silicon and carbide powder, and what we sell to our customer is a final module that he puts in the electric car, for example, or anywhere else. So from the PVD, crystal growth, to the substrate production, epitaxy, device fabrication, packaging, and module assembly, we do everything in-house. It's called vertical integration. We think it's a good approach. A couple of years ago, during the COVID, it turned out that supply chain is very vulnerable towards any global disruptions. So it's there's tendency to put everything back, at least partially, to Europe and US, not to put ourselves under risk of a supply chain disruption again. So now to the silicon carbide epi itself. Again, I don't need to go into details regarding polytypes, regarding the stacking sequence, and other things that are shown here. I'll point out to so-called Valiga figure of merit, which is some kind of quantity that reflects band gap, mobility, breakdown field strength compared to silicon. And we can easily see why 4H silicon carbide is the material of choice for many power switching applications. Also, as was already mentioned and nicely described by Ondřej, it's a material that is not identical when we turn it around. It has a carbon phase and silicon phase. The silicon phase is the one that is used for the device fabrication. It has a lower surface energy, and therefore it also has a smoother surface, less defects. Negative is that for the epi, the growth rates are lower, but there are less defects. So that's why we use it for epitaxy and for device fabrication. The carbon phase is mechanically harder, it's difficult to polish, it's more chemically reactive, and has more defects. So it's a backside C phase and front side of silicon carbide wafers is silicon phase. Regarding epitaxy, in the recent years, the 6-inch substrates are achieving pretty good quality, and 8-inch substrates are now being significantly improved. So we expect that in the coming years, the industry will switch from 6 to 8-inch. It's a natural evolution. The difference is that 6-inch substrate, you can see, has an orientation flat, while 8-inch substrate, we don't want to waste material. So similar to silicon, it doesn't have flat, but it has a notch, small one, which is not visible here. It's still not very mature, still expensive, but the progress is pretty fast. There are already many suppliers of such wafers. And regarding epi itself, what we want to achieve is a polytype replication. So we have a 4H silicon carbide, and we want to grow 4H silicon carbide epi layer 8. We use the off-cut to achieve that. If we have a surface of the substrate parallel with 001, then the stacking sequence doesn't need to be preserved because the atoms can incorporate in a different way. But when we have this position where atoms can incorporate defined by the surface as well as the stack, we replicate the polytype. Here it's a 6H, but it doesn't matter. It works universally for each one. So for the process itself, it uses pretty high temperatures, above 1600, lower pressure, hydrogen as a carrier gas. Growth rates that we achieve are in order of magnitude tens of micrometers per hour. And we use nitrogen for N-type doping. The precursors for the epitaxy are for the carbon, usually ethene and propane, or one of them. For the silicon, it's silene or trichlorosilene. When we use silene, it's convenient to add HCl because when the concentration of silene is increased, it tends to form silicon droplets or clusters already in the gas phase. So when we add HCl, it's a similar like silicon epitaxy. When we add HCl, we can form more, we can increase growth rate. For the nitrogen doping, nitrogen is conventionally used, but ammonia is also convenient to be used. I will explain later a little bit about that. Here's the comparison to silicon epitaxy. It's really very different compared to silicon carbide epitaxy, much easier. Because for the silicon epi, we only have heated holder with the substrates themselves, and the gases that we flow into the reactor only decomposed on the hot surface in the reactor. The rest is cooled down, which means that we don't grow any deposition on the sidewalls. we don't have our chamber dirty, and we don't have like auto-doping and other side effects. The process is stable, and also the temperature that we use for silicon is 1,000 to 1,200 centigrade, while for the silicon carbide, the temperature is much higher. And if you would like to build a silicon carbide epi reactors in your home, in your garage, you couldn't build it like this, like with cold wall. It has to be the hot wall type reactor. So the entire process chamber is heated up to the temperature, not only the substrate, in this case it's here, from the bottom, but also the whole chamber is heated on the sides. In this case, gases flow down to the substrate and the epi layer grows there. The negatives are that obviously silicon carbide doesn't grow only on the substrate, but also on the sidewalls. You can see some examples here, what it looks like, the sidewalls in the reactor, at the bottom, next to the substrate, even on the injectors. So the reactor gets dirty. We have some background doping. The process is not stable, it drifts. We have to compensate, not every run, but very often we have to change the recipe to keep the epilary parameter stable. And such equipment is, of course, more expensive than this equipment. And also substrate. In terms of silicon, it's defect-free. In terms of silicon carbide, not. A lot of these defects are then transferred to epi. Some of these defects we can screen out, convert, but many of them we cannot. As a result, cost of the substrate and epi process is higher than cost of the device fabrication, which is not the case for silicon. For the silicon, substrate and epi is cheap. For the silicon carbide, it's support. We are those expensive guys. We are those that make the technology expensive. So obviously, we want to achieve high growth rates for silicon carbide. We want to produce a lot of wafers in a short time. So the throughput of our equipment is high, and we don't have a high price of wafer. This can be achieved by simply flowing more precursors into the reactor, but it has its limitation in the silicon clustering in gas phase, so we cannot infinitely increase flow of TCS and propane or ethene. The other parameter that we can tune is the thickness of boundary layer. Boundary layer in epitaxy is the layer or stagnant flow layer where the gas flow velocity is reduced or stopped by the friction of the gases with the substrate, and precursors and reactant species get to the substrate by diffusion through this layer. And the thinner it is, the higher is the growth rate. We have these horizontal type epi reactors where gases flow horizontally, and here we can reduce the boundary layer thickness by flowing simply more gas, having faster flow. But again, we cannot do this infinitely because otherwise we would need huge pumps to pump down the flow, keep low pressure. And in the vertical reactors where gases flow vertically to the substrate, we can rotate the substrate very high RPMs, and we can again decrease thickness of the boundary layer. So here's the typical epi stack that we grow on a silicon carbide substrate. The substrate is here basically to hold the epi, because all the device is then fabricated in the epi. So this is a little bit exaggerated. Of course, it's not ballast, but really it's there just to hold the epi, just to make something we can grow a good epi layer on. For the substrate, we need to avoid any damage. We need to avoid any particles, roughness generation on the backside, scratches, and so on. So that's something that's very different from whatever you do at the universities, academies, because you take samples, you put it somewhere, you care about the front side, polishing, epi layer, and so on. You don't care about the backside. We have to care about the backside as well. It's important because guys in the fab take it, load it into the different different equipments to make the devices. And the backside is kind of a reference for the process. On the backside, it holds. And if there is some cracked backside, some dirty backside, it just doesn't work. The procedures like a lithography, it doesn't work properly. So we have to avoid any damage on the substrate. Then for the epi process itself, we start with the pre-etch. We prepare the surface, clean out some chemical contamination or small particles. It's simply done by exposure of the surface to hydrogen, atmosphere, eventually HCl can enhance this. Then we start to grow the buffer layer. The buffer layer is important there to reduce defects and convert some defects which are bad for the device to other defects which are much acceptable. It usually has a lower growth rate and different parameters compared to the rest. And the rest is defined by what the device is going to be. So this is defined by device guides. For the MOSFET, typical spec is composed of two layers, the layer and the drift layer. Drift layer is the main one that defines parameters of the device. The higher is the voltage of the device, the thicker it needs to be, and the lower doping it needs to have. Here, the main goal is to control the thickness and doping of these layers as well as possible and maintain low defectivity. There is an example why silicon carbide is more suitable for high power devices. When we want to produce, for example, 1200 volt device, we need to grow 100 micron silicon layer with some doping concentration. When we do the same with silicon carbide, then it's 10 times thinner and 10 times higher doping concentration, which means that the resistance of this layer is significantly reduced, overall reduced. So the process parameters that we control. First is thickness of the epi layer. Very simple approach. We have some precursor flow, growth time, and this gives us target thickness. So we want to keep the average thickness on the wafer as close to the target as possible. And at the same time, we want to be the thickness as uniform as possible across the wafer. The parameters that are controlling this are mainly carrier gas flow and carbon to silicon ratio. Carbon to silicon ratio, you will see on the following slides that it controls pretty much everything. It has influence on pretty much every parameter. The temperature, we mostly want it to be uniform across the wafer. We want to avoid some thermal stresses across the wafer and also high variability. So when we flow the gases from the injector towards the chamber, there is some kind of depletion profile. The depletion profile tells us something about the growth rate, distribution across the flow of the gases. And somewhere here we place the rotating wafer. And therefore, in the wafer center, it's more or less stable growth rate. At the edges, we alternate between the high and low. So this depletion profile can be tuned by the total flow of carrier gas as well as by CSR ratio. And here are a few examples. If we don't flow that much gases into the chamber, then we have this peak shifted towards the inlet, and the resulting thickness profile is kind of U profile. If we flow more gases, we shift this peak towards the exhaust, and we have kind of a shape. What we want to do is to find some optimum and achieve as uniform thickness across the wafer as possible. Usually it's slightly M or W shape. So there are some other gases, the precursors. We have a precursor for carbon and silicon. The one that defines the growth rate is mainly in silicon precursors, so silane or TCS. You can see that the function growth thickness as a function of silane flow. That's quite strong dependence. The three different curves correspond to the three different propane flows. You can see that the influence here is not that large. The temperature also has influence. The lower, the higher thickness, but there is limitation. You cannot decrease the temperature infinitely because then you are out of the optimal process window for defects and other things. And it also varies between the different epi reactors. So the second important parameter of the epi layer is the doping. This we can easily control with dopant flow, how many dopant we flow into the reactor. The doping concentration is very sensitive to the CSI ratio, and that's because nitrogen sits on the lattice place of carbon. So the more carbon is there, the less nitrogen can incorporate into the lattice. So when we decrease the CSI ratio, for example, shown here, when we decrease the CSI ratio just from 1.1 to 1.7, we have almost 2 orders of magnitude lower doping concentration. So it's something that's very important, and it's also kind of dependent on the epi reactor that is used. Every epi reactor has a different optimal CSI ratio, slightly different optimal CSI ratio. So we always need to have calibration curve for the different doping flows. We always need to have a calibration curve for the given CSI ratio. Again, typical doping profile across the wafer depends on CSI, not only the absolute level, but also usually the profile. So again, optimal CSI ratio needs to be found to keep the doping as uniform as possible. The calibration curves I talked about are, for example, here, from 0 dopant flow to some high flows, you can see pretty linear dependence. So breakers of flow shows linear dependence, but the CSI ratio is strongly nonlinear. Regarding defects, we have already seen some things from the previous lecture. So we have 0D, 1D, 2D, 3D defects. Basically, the dislocations can be of various types: trailing edge dislocations, trailing screw dislocations, and then the basal plane dislocations, so-called BPDs. The 2Ds, the most important, are stacking faults. There are many different types of stacking faults. 3D defects are those that are most harmful to the devices, such as the micropipe fusions, triangular defects, and some others. The examples are here. The defects are well known, well documented, but that doesn't mean they are well controlled in the epi process. It's not easy to control them. In some cases, especially those that are inherited from the substrate, most of them we cannot diminish by the epi growth. There are a few that we can, but most of them you can see that this evolution of the defects goes from the part material towards the epi layer. What we can convert is a BPD, which is partially harmful to the device, to TEDs, which are less harmful. So the dislocations, TEDs, they are not a problem for the device. TSDs, they are a problem because they can negatively affect the device performance, and also they are usually, or not usually, but they can result in nucleation of other defects during the epi growth, such as the stacking faults. The BPDs, they usually have thousands of them per square centimeter in the substrate. In the epi, we are able to convert them to TEDs. And the conversion efficiency is as high as 99.9%. The mechanism is played here. When we have a BPD, and imagine that there is a step here, and then we grow the epi. If the step flow growth prevails, then the BPD propagates. We are able to make such a growth conditions that lateral flow, lateral growth prevails. Then we kind of close the BPD here and convert it to TED. This is a TEM image of 2 BPDs that here are converted to TEDs and continue as a TEDs. DEDs are pretty much harmless to the devices. So that's what we want to achieve by the buffer lane mode. The growth conditions that we choose to achieve this are lower growth rate and lower CSI ratio. There are parameters that promote this kind of lateral growth. Okay, structural defects, the defects that are 2D or 3D, the stacking faults, they can be played from other dislocations. We don't see them physically by microscope, but we see them, for example, in a photoluminescence. They look like B-star triangle in the photoluminescence signal. Then there are partial dislocations. They kind of border the 2D defects, such as the stacking faults. And regarding stacking faults, there are many different types. Right now, we don't distinguish between them in our metrology, but that doesn't mean that they're all the same. They can have different effect on the devices, which is something that should be addressed in the future. The extended defects, especially the triangle defects, you can see them here, for example. They are bad for device. There is always some optimal process window in terms of a CSI ratio and growth rate where we want to stay. If we have too high CSI ratio, we end up with many triangles. And if we have too low CSI ratio, which means we have a lot of silicon, there, excessive concentration of silicon, we end up with droplets in the surface. These are examples of the triangular defects. They're basically different polytypes and caused by some local interruption, local disruption. For example, when large particle is present on the surface, then the locally step flow and polytype replication is interrupted, and the different polytype starts to grow there. You can see very clearly by any type microscope and also in the photoluminescence. When any chip has such a defect inside, there's almost 100% probability that it fails. The killer defects, this is a graph showing defects per die and the probability that it fails. And once there is 1, 2, or more defects, the probability that it fails is almost 100%. So that's why we need to very carefully measure these defects, and we hand over this information about the location of every single defect like this to the fab. And in the fab, they know that if they fabricate a chip at this place, that the chip will fail. So the technology for mass production, I mean mainly epi reactors. Here you can see from a yellow study what are the manufacturers of the silicon carbide epi reactors. Those that are most important with the highest market share are LPE, Dell, Dufler, and ACDRC. This will be slightly changing in the coming years. It's only 2022. Some of these are worse, some of these are better. And chip makers like us usually have more types, because now it wasn't clear which design of the reactor is the best. Now it's becoming more and more clear, so some of these will lose their market share very soon. I'll describe briefly 3 types of the epi reactors. First one is from Japan company Dufler. It's a vertical type reactor, so there's a quite complicated injector on the top, and gases flow down to the substrate, which rotates at the high speed. There is a resistive heating both from the bottom and from the sides. Advantages, it has a quite high growth rates. You can kind of switch between 6 and 8 inch configuration kind of easily. Disadvantage is that it's quite complicated reactor, and also the high rotation speed and the rotation mechanism is not mechanically very robust. Then the ACDRC, based in Germany, using some of their tools in presentation from Alice. for the gallium nitride, but they also do equipment for silicon carbide. They use the planetary system, which means that there are multiple wafers placed on the main disk, which rotates, and individually every wafer rotates as well, kind of a planetary plant. So it's a horizontal type, it's a batch reactor. The hardware is also quite complicated, but at least it has a RF heating, inductive heating, and because it's a batch reactor, it has a pretty high throughput. We can produce a lot of wafers with this type of reactor. And that's despite it has a lower growth rate compared to its competitors. Then Italian company LPE recently acquired by ASM. It's also a horizontal type, single wafer reactor. It has quite robust, simple design. It's just a chamber with a rectangular cross-section, rotating substrate, gas flow horizontally. It's pretty easy to switch between 6 and 8-inch configuration, which is something that's very important for us in the industry. It has an excellent layer uniformity, and also the process is quite stable in this reactor. So if you want to buy some epi reactor, I can recommend you which one you should buy. Just let us know. This is a diagram of how we control the process to produce silicon carbide epi wafers. We measure 3 basic things: thickness, doping, and the surface defects by a dedicated tool. There is a specification that tells us this is where you can be with your product, with your thickness, doping, maximum quantity of defects. But we always have to have some control limits that are more strict. And once we are outside of these control limits, we have to do something with the recipe or with the process or make something. Once we are even out of a specification, we have to put the tool down, make maintenance, clean it, investigate what's the problem, and so on. So the entire processing flow on the epitaxy is starting after epi with the visual inspection, then thickness measurement, doping measurement, wafer cleaning processes, and the final inspection and defect classification. Obviously, we have some multiple layer stack here. We cannot measure doping in all layers. We only measure doping in the top one. We measure thickness of the entire stack, so we cannot measure individually. So again, if we want to check buffer and the second layer, we have to grow dedicated wafers. We have to do this regularly to keep also these layers in specification. Now, briefly to the metrology. So the doping is measured by mercury CV. We have pneumatically controlled contact with surface realized by the mercury. So it's a contact method, but it's theoretically non-damaging. It's quite stable and repeatable, but it has its disadvantage because obviously you need to make some contact. In terms of thickness measurement, we use a simple method, FTIR spectrometer, basically infrared reflectometer. And what we get is this kind of interferogram. And from the position of the side bursts, we can directly read the thickness of the epi layer. This method has its disadvantages and limitations. Professor Humlíček knows about this very well because he was helping us to uncover some of these limitations of this method. The advantage is that it's robust. When we take one wafer and measure it 100 times, we will get the same result on nanometers. Repeatability is really great. Measurement of the epi defects. We have two from the company LaserTech. It's basically there are many manufacturers of similar equipment, and what it does is that it very detailedly photographs the surface. It makes an inspection, very detailed inspection of the surface, and in addition to the visible channel, it also collects the photoluminescent signal. So different defects have a different appearance in the visible and in the PL channel. For example, those triangular defects, you can see them very clearly in both channels. But stacking fault, you don't see anything just by the visible light on the surface because it's just the 2D defect, but it does have a signal. Similar to BPD, we can see basically in this location as a bright line in a 1, 1, minus 2, 0 direction. So once we have such an inspection done, we can plot the map of every defect we want, every defect we classify. And some of these defects, as I mentioned, we classified as the killers. So when we have a wafer with some chips, the chips might have different size, few millimeters by few millimeters. And when we plot this chip map and overlap with the defect map, we can predict what is the percentage of chips that will be good, that will be functional. And that has its specification. Once there is more defects, there is a lower yield on that wafer, and basically the product is out of specification. So the last part, evolution and challenges in the silicon carbide EPI in recent years. In terms of pure scientific evolution, there hasn't been any breakthrough, I would say. There's a steady progress. Things are being published in terms of defects, in terms of devices, in terms of crystal growth, and so on. But there hasn't been some breakthrough. In industry, the situation is opposite. The evolution has been really very dynamic in the recent years. And I don't mean only transfer from 6-inch to 8-inch, but basically in pretty much everything. I tried to make some, I tried to express the evolution somehow from our standpoint, from how we see it when we do it. Czech people know very well this car, Škoda Favorit, 35 years old car. It could transport you from one place to another in some time. It probably wouldn't get you killed, so on, but the trip wouldn't be very comfortable, and quick. But this is basically how I see our EPI mass production when we were starting with it. And this is what we need, where we are almost today and what we need basically next year. This is Škoda Enyaq. So 35 years apart, but for us it's like 3 or 4 years. This is kind of evolution that we went through. Yeah, by the way, fun fact. Do you know how many chips were in the Škoda Favorit? Try some guess. Any other? I hope I'm not mistaking this with Škoda Felicia. I think it was Škoda Favorit, but there were two. One was a starter, and the second one was radio, if there was radio.
Okay.
This one, give me a number.
100.
Can you drive from Rožnov to Brno with the green one?
Yeah. We are doing it. We have a company car, Škoda Enyaq. 1,000, 2,000.
Hundreds, higher hundreds.
Higher hundreds.
Yes, so.
6,000 sensors in 6,000 objects.
5,000 or 6,000, I don't know exact number, but
Okay.
And by the way, look around. All the laptops or the mobile phones, here,
Yeah. Everywhere.
You are surrounded by thousands of chips. It's interesting sometimes to take a moment to realize what is our world today and how it evolved. Okay, but back on the board. So in the 2021, we in Rožnov started to install first equipment and make process development and qualified first products. We pretty much had this kind of things automated, like we didn't have to take the wafer physically and load it somewhere. It has a automated cassette to cassette handling and so on. But everything else was pretty much done manually, calculated manually, and input into the reactors and recipes. Here we are now, we are on track on the full automation. So all these control limits, specification limits, and things are controlled automatically. And soon we will also have recipe automation. So in the industry, you have to kind of integrate every tool into your IT infrastructure. And when you succeed with this, you can do the same work, not with 20 people, but with 3 or 4 or 5. So also in terms of maintenance of those reactors, Alisa mentioned how they need to, after every run, clean up the reactor. Yes, we still have to open the reactors and clean up all those depositions and so on. There are many parts that needs regular replacement, but how do we know when to replace those parts? Of course, we need to have some statistics and predict when it fails, but some things can be done in a smart way. For example, when you have heaters, resistive heaters, their resistance is increasing in the time and then they fail. So now we know when they fail and we can monitor the resistance automatically, and equipment guys can see, okay, there's warning limit within 5 or 6 following runs, this part will fail. So I will plan the maintenance. I will do the maintenance tomorrow morning, and we avoid like losing the wafer because of fail in the middle of run. Also, interesting thing, we have worked on the improvement of the doping control. This table shows bond energy of the precursors used in the process, as well as HCl, and compared to the nitrogen molecule, it's all lower bond energy. So it's difficult to thermally decompose nitrogen molecule, but when we use ammonia, it's much easier. This means that we don't have to flow excess of nitrogen in the chamber. We don't have a background then in the chamber incorporation in those walls and so on. And if you take a look at the variability of doping, just by changing the process, it's not that simple. It's a lot of work, but by this change, we can achieve much tighter doping control compared to POR process that we had before. Requirements for the thickness and doping. They are driven by the requirements from device guys, which are working on the new generation of MOSFET devices. So these devices have a more complicated design, and requirements for the control of doping and thickness of epi become more and more strict and more challenging for us. For example, we have some specified average thickness and doping on the wafer that we need to achieve, and some specified variability of these parameters on the wafer. Before, we were specifying this with a sigma over mean, which had to be smaller than some value. Now, the requirement is that it has to be max minus min over max plus min, which is basically twice as strict compared to the previous one. Regarding the average, we used to have some target plus minus some percentage. Now this plus minus percentage is reduced to half or even third. These graphs are showing ticket simulations of device breakdown voltage and resistance as a function of thickness and doping. You can see that if we have a high doping and low thickness, we end up with a low breakdown. And if we have a low doping and high thickness, we end up with the high resistivity of the device. Both of these are bad. And looking on our thickness and doping profile across the wafer, and this is the wafer center and this is towards edges. The red one, for example, wafer edge, we have low thickness, high doping, we're in the bad corner. Just a few millimeters next to it, we have a high thickness, low doping. We end up again in the bad corner for that's because we have opposite profiles. Here we have M, here we have W, goes against each other. So what we did is that we optimized the doping profile to be similar to thickness. And immediately we improved, for example, breakdown distribution on such wafers to much tighter distribution compared to the old process, and also average value went up. I mentioned that there is a trend to go from 6-inch to 8-inch. That brings some additional challenges for us. I mentioned the carbon to silicon ratio is a very important parameter. The carbon has a lower surface mobility compared to silicon, and for some other reasons, the carbon to silicon ratio is needed to be higher than 1, which means that the silicon depletion is that there is a silicon depletion effect across the flow direction. So if we start with some higher amount of carbon atoms and lower amount of silicon atoms, they are consumed more or less equally. This means that as we go in the flow direction, we end up with a higher effective CSI ratio than we had at the beginning. So again, higher or bigger substrate, more challenging for the process to control, because at this distance we have a higher variation of the parameters that are important for process control. Thickness measurement, I mentioned that we had some problems with this. If you take a look at this interferogram and these side bursts, what peak should we take? Always the highest one, right? But what if the two are pretty much similar height, pretty much similar magnitude? Then the two can be confused, and it can once take this one and another time take this one, which means that measured thickness might not be correct. Second thing is that looking on the SIMS profile, from the substrate to the top layers, we have this kind of step structure. So buffer layer is order of magnitude lower compared to substrate, and again order of magnitude lower layer. But what if this buffer layer accidentally has a higher doping concentration close to substrate? It means that in the interference, we don't have reflection from this interface, but maybe. And again, we don't have information about thickness of the entire stack buffer. So we might want to change our method of how we evaluate thickness on FTIR. Today you have seen this spectra. Professor Humlíček was showing this. It's a reflectance spectra. When we filter out only these higher wave numbers, we can basically do FFT, and we can directly see what's the thickness by doing FFT of this filtered spectra. And this is in good agreement with other methods such as SIMS, spectral reflectance, optical measurements done by Professor Humlíček and his team. Another thing that we are considering for the future is if we can measure individual of these layers, not only the whole stack. Maybe we could, if we do modeling of this reflectance spectra, we probably could discriminate between buffer and the rest. We could also extract the free carrier concentration from the buffer as well as substrate. I'm slightly over time, so I will skip this one. I will just mention that for the doping, there is also possibility to measure doping with a non-contact method. It's called CNCD. The bias is not applied by the bias applying to the contact between the mercury and substrate, but by corona discharge applied without the direct contact to the surface, and then there's a vibrating Kelvin probe. And again, we can extract doping concentration from this. I will also briefly comment on the defect characterization. So when we do this evaluation of the filter defects and prediction, what percentage of chips will be good on the substrate, we have some internal limits. So there is some best class of the wafers as yield, then some slightly lower, moderate, and something which is below some limit, which is not acceptable. That was situation in basically the beginning. Now, when we take a look on the same numbers, device guys from FET look on us and they tell us, don't you dare to be far away from 100%. We only want this, and nothing which is lower is acceptable, is not acceptable anymore. So naturally, with improvement in the killer defects, the known killer defects or the other defects become more important, such as the stacking faults, partial dislocations, and so on. They are not killer defects, so they are there. They don't make your device non-functional, but they change some of the parameters of the devices. For example, they can increase leakage current, which makes issues for your breakdown voltage, threshold voltage, and so on. For evolution of this, we need to have a lot of wafers produced and processed in the fab and feedback from device guys to make some another specification and set the limits for other defects, not only those triangular defects, but also other. So that's pretty much all. I'm slightly over time. I'm sorry.
No problem.
But thank you for your attention.
Okay, thank you very much for the presentation. Well, that was the industry overview, point of view on wide bandgap semiconductors. So questions can ask you. Okay.
I missed the scale bar on your, which is a killer defect. So what is the size of the defect? Is there a critical size that becomes detrimental?
The size of the killer defects is simply given by the thickness of the epi we grow. When there is the defect at the beginning of the epi, like big particle or some defect from the substrate, because of the offcut for 4 degrees, it grows to certain width that is defined by the thickness of the epi. And simply by calculating thickness over tangents for degrees, you can calculate what will be the width of this. So this dimension is defined by the. If there's a big defect, and maybe we have this chip map. So we have chip map or real chips. If the defects would be such a large that it intersects 2 chips, then both of these chips would be scrapped. If the defect size is that it only is 1 chip, then the 1 chip is scrapped. But we measure it, and we know what's the size of the defects. The tool can automatically classify it, and the information about its size is basically coupled with the position of the defect. So in the fab, they know exactly where the defect is and what is its size.
Okay. Yeah.
So I'm not sure maybe if I missed it, but what are the critical parameters of the substrate for epitaxy? Like, for example, the roughness or the defect density, or what defects in the substrate are so critical?
Yeah. In the substrate, the defects that are monitored and classified, there are less defects that are monitored and classified compared to epi because they're not so well visible because of the high doping concentration. But the main defects are micropipes and then various polytype inclusions, particles that are not removed by cleaning and so on. But maybe you were more referring to the pack quality, which is something you don't measure on the substrate, but on the pack level. When the pack is fabricated by the PVT, then there is usually some sample wafer taken and processed. I won't go into detail, but basically dislocation density is measured, trading edge dislocation, trading screw dislocation, basal plane dislocation, micropipes, which we can measure on the substrate as well. But the micropipes are already measured on the pack level. And there are some specifications for these. And if the pack is worse than the specification, substrates are not fabricated for this. If the pack is okay, substrates are fabricated and again measured. And then there is a specification for micropipes, particles, polytype inclusions and some other defects. So you can see a list of some defects here for the bulk and the substrate that are measured and controlled.
And concerning the polishing, I mean the roughness of the wafer?
Roughness is something that is not measured routinely on the wafer. It's measured usually during the qualification of the tools by AFM. We can partially evaluate roughness again by the optical measurement method with these tools, because what we see here is kind of a dimensionless map of the haze of how light is scattered from the surface. When there is a high roughness, a lot of light is scattered, like not like reflected under expected angle, but scattered. And when roughness is higher, a lot of light is scattered, and this haze is like higher. It's dimensionless, but we can correlate it to, for example, roughness measured by AFM. So it's something that is not directly specified, but something that is monitored and optimized to be good during the qualification of the processes.
Okay, maybe Veronica.
Again, you mentioned the yield. It is sufficient for you. A different yield for 6 and 8 inches wafers?
Not really. We have to achieve the same or better parameters on 8-inch as we achieve on the 6-inch.
Is there a problem with the yield in bigger wafers? Because we know that there's a problem to make bigger cuts or wider diameters. So
we selected EPI tools in such a way that the process is good on 8-inch as well. On the PVT side, in the pack fabrication, it's more complicated than on our side. It is more difficult to grow large crystals compared to small crystals. For the EPI, it's not that big problem like for the previous steps, like for the pack production and substrate production.
Okay, and
I didn't catch if you have all 3 types of photo epitaxial apparatuses, because you said ask us about, so you have experience with all of them?
short answer, please. Short answer.
We have experience with more than this.
With more than this, so you have even more apparatuses.
I'm not saying we have these and we have more than these, but we have experience with not only.
And another question, because there are different polytypes, do you think, I know the for most transistors it's out of any thinking, but do you think sometimes there would be heteroepitaxial, like combining different polytypes and making quantum walls or something like that?
That is interesting thing, and I believe that many groups worldwide are working on something like this.
Okay, so I see there will be a lot of other discussions and questions. We can continue within the networking dinners. But once again, thanks a lot for the presentation and discussion. And we will proceed. Last but not least, okay, so another view on the semiconductors and silicon carbide from the huge producer of electron microscope and the representative Libor Strakoš. Very happy to have him also here. Libor is in general our graduate from our faculty, so we are very happy that also from our university, we have the representative here. So, yeah.
Thank you.
Thank you very
Thanks
much.
a lot. So I will not speak only about electron microscopy. I will also speak about other techniques. I think, you know, today's workshop is a great example. I will fast forward here before I go back, but you know, as kind of the motivation from the beginning, we've seen, you know, basically what we kind of show in when we want to popularize semiconductors is that we show, hey, there are, you know, 3 major phases in the life cycle, and there is, you know, kind of the pathfinding R&D, that is a yield line where you want to take what you developed and kind of start to manufacture the devices in a more repetitive manner, and then you have a failure analysis. And throughout the day, you know, we started somewhere over here, and then in the last talk we've been moving through this, and randomly I selected this as my topic for my tool. So for my talk, so you will get full picture today. So also kudos to Jiří for maybe not intentionally, but planning in such a way that it really makes sense to start here and end up at the end, where actually we have a failure. But also, you know, I will guide you through failure analysis of semiconductor devices, especially, you know, I will give examples of wide band gap. I have also a courtesy to be member of vendor feedback towards failure analysis roadmaps, meaning I will not do a product marketing of ThermoFisher here. I will more general speak about the challenges and how to address the challenges moving forward in failure analysis, because this is what we kind of agreed on the vendor roadmap level when we collected the feedback from guys like onsemi and many others, how we are about to tackle the challenges they stated they will have moving into the future. So still, it's going to be electron microscopy and some of the adjacent techniques, but it's going to be very relevant to this crowd and to wide band gap at the end. So key takeaway, you know, if it's not clear yet, it's really something simple. Electron microscopy and the techniques, it's really a critical technology to sustain the semiconductor industry roadmaps, regardless if it's on the research side, regardless if it's on ramping the production, or regardless if it's on the failure analysis. And we see more and more volume of electron microscopy analysis, and also some of the adjacent techniques is growing, and the importance is growing, and you know, also our install base is growing. So that's one of the indications. So there is a lot of challenges with failure analysis. I think the first challenge is the definition of the FA, but I will really for today's try to stick to the fact that, you know, there is already a device which is manufactured and, you know, to some extent functional, at least on the electrical level, but there is a failure. So it either does not pass electrical testing, or it failed when it was exposed to the real environment, or maybe what is worse, to the real user. And each of the, you know, segments has its own specific challenges, and wide band gap has a very unique set of challenges. And I think it was seen through today that while for the, you know, for the logic and memory, the dominant thing is, you know, dimension of the structure, integration of the heterogeneous devices altogether, which is more on the packaging side. For wide band gap, this really stays on the material level. And so the material properties are now the major driver of the failures. And we've seen a lot of similar graphs today, but the outcome of that is, you know, there is a superficial performance of these devices, but it does not come for free. It's difficult to manufacture them. It's difficult energy-wise, and it is a, you know, it's more complex. So it comes with more defects. So for us, it means that there is a more FA coming alongside to be able to resolve it. So just to also see it from the other side, even though the physical and electrical properties are great, it also comes at the cost of the challenge to be able to produce the devices, to maintain the quality, and so on and so on. So today, as we move through the talk, we will move on different scales. So the only thing which is not semiconductor here is the human hair, just to see where we start, because we will really start for something which is visible by eye, but we will slowly move through the devices on the level of the transistor, the epi layers, quantum belts or superlattices, down to the crystalline structure. And we will speak about failures and how to localize failures on these levels. So I spoke about the definition of failure, and obviously we spoke today a lot about substrate, a lot about the substrate with epitaxial layer, and we did not get yet to the level of the device. This is what I will focus on today. So, as I said, there are unique challenges with the new architectures, and I will speak mostly about the MOSFET. The biggest challenge for a wide band gap is that the devices has the metals on the top and on the bottom, and this means it blocks photons, blocks visible light, or blocks light in general. The structures are large, and you cannot use the trick as the silicon device manufacturer used, that you can essentially look from the backside. I mean, that thing is already gone in a couple of years from now, because they will also put metal delivery network on the bottom of the devices. But this is what causes the challenges, because traditional approaches for localizing the failure in such structure becomes more difficult. And what it means also for localizing the defects of any type, let's do not stick to the defect in understanding of, its crystalline defect. It's whatever which causes the device to fail. It can be, contamination. It can be wrongly deposited layers. It can be even wrong dimension of certain structures. There is a lot of flavors there. And it's not a simple task to localize failures on the device, which is already done, because it's really or manufactured and functional, because it's really a detective work, and typically you use a lot of different modalities, and you see, that you can say electron microscopy is over here and over there at the end, but in between there are techniques which has nothing to do. They have nothing to do with electron microscopy. Yeah, these are just examples, how it looks like. It's a lot of different boxes doing different things. But if you want to actually find the root cause of the failures, you have to have that equipment if you are a manufacturer. And I don't know how far the tour of onsemi will get you tomorrow, but they have a lab and they have this kind of equipment over there, because they do these things as well. So let's come back to the challenge. So, if you have the defect, I think we've seen already a similar image in here. So if there is a drive, or we drive voltage, or we drive current through the device, if there is a fault, you can see it. You can see it with the thermal camera, so you can see the hotspot. Somebody already referenced it in the talk before. The challenge with that is you have you look from the top, and you have metal structures on top. It means that it conducts heat, and the thermal path of how the heat dissipates through the metal means that you are not able to do the localization very precisely. So if you take a look over here and over there at the corner, you see that actually, if you use different techniques, either the thermal camera or visualizing the resistivity change, you see there is a mismatch by the position it's made by the physical properties of the particular modality. But you want to localize the X, Y, Z of the defect precisely. Otherwise, you are not able to do it because at some point you will want to get destructive. So you will need to cut inside the device or remove some material. And basically the defect itself is the only data you can collect about the defect. Once you destroy it, your snapshot of the defect is gone, and you cannot drive. You will not find the root cause, and you will not able to drive corrective actions and feedback to the manufacturing. So as the stack of the devices is quite unique with respect to wide band gap, the challenge there is you have a thick metals at the bottom. Basically what you want to do is you want to remove. Originally my slide was in PowerPoint and there was an animation, but you can imagine that suddenly this part of the image disappears from here to top. And this is what you want to, in a very controlled manner, remove. Because what you do by the removal, actually, when you remove, you improve the positional accuracy of your fault isolation techniques because you remove the heat dissipation path of the defect. So you localize more precisely. Now, the challenge with that is that you go through a stack of different metals, and you are using because it's only we call it thick, but in reality it's like 1-2 microns of the metals. And this is where you are already at the edge where you can use like a mechanical polish or mechanical removal of the metals. So you move forward with something we call plasma focused ion beam delayering. You basically use accelerated ions together with the chemistry to get through the stack of metals. So you are able to get a planar surface on top of your device. So what you see here is the challenge. If you don't use the chemistry, there is a problem because the ions have different sputter rates for different materials, and you will not end up with the even surface. So you need to enhance the delayering process with using the chemistry because what it does, it basically homogenize basically the response, or it drives more of the chemical portion of the etching, and then you can end up with the planar surfaces. Why it's important, I will come to that. The goal of that is that you assume at this point that your defect is in the active area of your device, and you want to keep your device still functioning at that point. So it means that even though you remove the material from here, the device still works. So you can still come back with your beam resistivity or lock-in thermography measurement, and you can precisely localize the defect. So it's also an iterative process because it's not only about X, Y, it's also about Z. So as you move forward, you delayer more, you measure with the optical or thermal fault isolation systems, you also improve the precision of your fault isolation. And ultimately, if you want to really precisely locate the defect at the end where you reach the location of the active device, you can contact your source, drain, gate, and you can actually test even IV characteristics of the device and see which ones are failing. And you can also see by electrical measurements where the defect is, because you will see different response at that point. There is a whole set of techniques, obviously, how to measure that. And the question is what happens then? So you have localized tailor through that iterative process optically and electrically, but now you need to proceed with some type of analysis which reveals the defect and tells you, what the defect is. And remember, the defect can be anything. It can be even crystalline defect. It can be failure in the dopant profile of the device. It can be wrongly deposited material. It can be contamination. And, you know, at that point, your idea about what type of defect you are looking for is limited. I mean, you have some signatures already through the process, but it's limited. So what you can do at the location of your defect, so you can do a couple of things. There is more things you can do, obviously, but this is kind of the industry standard type of analysis, which is then tied to electron microscopy. You can use the ions to cut through the device and look at the cut face and see. This is more on the structural type of the analysis. But once you expose the location of the defect, and you are not able to see something which we call like physical defect, so you can really see that something is wrong in the image, you need to proceed with some type of electrical measurement. So the alternatives, you know, there is a couple of alternatives. What I listed here, you can take a look on the dopant concentration, or you can really do, you know, microsurgery, or more like nano microbiopsy of your device, and you extract the particular failed part, and you go to even transmission electron microscopy where you have higher resolution, but you need to keep the sample very thin or transparent to accelerated electrons. And you need to also somehow be sure that this is the utmost destructive process, right? So you, at that point, you already made a decision that you want to take the risk because the analysis is worthy to, you know, do so much destructive type of analysis that you could easily destroy the defect such that you are not able to find the root cause. So for the cross-sectioning is, you know, so we see one thing, and in the usage of accelerated ions, we see some movement to use different ion species. So originally, you know, what was the industry standard was gallium liquid metal ion source. The problem with that is that there is a lot of aluminum in the devices. Gallium does not work well with aluminum. It's also a dopant, and it, you know, it also damages the crystalline structure. So we are looking also how to introduce other ions which could essentially help. And these ions are xenon, argon, but you can have more. And we are seeing that the argon so far works the best because it, you know, the best it preserves the something we call it like cut face quality, but in reality is how you do not damage the crystalline lattice of the structure. And also you can have very effective material removal rates with argon because you can use very high beam currents, meaning very high sputter rates of the materials. And also argon has a good advantage because the dependency on different material is less. So when you see some of the artifacts in here, these are caused by, you know, the microstructure, but also different mixture of soft and hard materials. If you look at the argon, it doesn't have that artifacts. The reason behind is that it has less dependency on the type of the material with respect to the sputter rate. So you can improve your cutting. And one other thing, this is really important for the industry because we spoke about the throughput. So if I rewind back that for the XRD, you know, it was said that on the level of the wafer, it is like 12 plus hours, right, to characterize. So we have, you know, the requirement we heard is we want the wafer be analyzed over the course of 1 hour to make actually a cut for us that we would consider this technique for the industrial use. So it's kind of, you know, you need to push the boundaries. And this is also why we are introducing, or especially in wide bandgap, we see a lot of adoption of different ions for removing the materials, because with respect to the traditional technologies using like gallium, it has by, you know, 1 or 2 orders of magnitude higher performance, which then means that you can come to your root cause significantly faster, and this brings value. So yeah, I spoke about it. This is a little bit of the example. You know, I said the argon then gets the best results. This is a STEMIN SEM image. Basically, we are looking at the individual atoms on gallium arsenide, and you see, you know, I don't know if it's visible, but you see actually that especially the signal to noise and the resolution is better. It's driven by the different properties, size of the ions. So second thing is, you know, the dopant profiling. It's been said that it's something which is very, very important. Now, one of the techniques is scanning spreading resistance microscopy. This is something which is typically used on the bulk or wafer level. But there is one company in here in Brno which is called Nanovision, and they have a scanning probe microscopy module inside electron microscope. And we did experiments with them that we can actually do the same thing on the level of the device. So what we can do, we can use our microscope to prepare the cut face and prepare the cut face. This was supposed to be the animation. This is a sharp tip which goes to the surface, and actually we are able to do SSRM measurements, meaning that we can use the probe which has you know, tip of the diameter of couple of units to tens of nanometers, really push it hard towards the sample surface, so the spreading resistance is the dominant resistance we measure, and then we drive current at the voltage bias through the cross section of the device, and then we are able to measure resistivity changes. And when we are able to calibrate it, which we are able to calibrate it, then we can not only visually see like qualitative changes in the resistance of the device at different structures, but we are also able to calibrate it and say how the dopant profile looks like. And you know, last one I selected is transmission. So transmission electron microscopy. This is really the, you know, kind of the last instance of the analysis, and this is very really looking for the defects at the scale of, you know, sub 10 nanometers, because you are looking for that kind of resolution there. So, you know, literally what you can do is, because it's a serial process, so, you know, everything I showed goes by the other, so it's a serialized process. So you can end up with your cross section that you are not able to say what the root cause is. You can still do at that point you can still do a biopsy of your device and kind of, you know, lift out the piece which you assumed is the one which is detected, and then perform some other analysis in transmission electron microscope. Now, the number and the volume of analysis and different modalities you can do is actually very wide. So I don't want to go through the full list. This is just to give you an example that, you know, if you kind of go blind, you know, it's for you, it's quite difficult to tell what analysis you need, because you can look at a different type of the defects or the challenges, you know, if it's, you know, epi-gate interface or nucleation or propagation of the defects, or even simple chemical analysis through EDS or bandgap. But I, you know, on purpose choose only one application, and it's the one because it's my personal preference. It's not like something which would be so much used, but I find it really cool. So little bit of introduction. So in the transmission mode, you can also run the microscope in a way that you position your beam into what you can imagine a single position or pixel, and then you can scan in the raster and measure the transmitted electrons in, and you can measure different types of the contrast. It's really not the purpose to discuss this here at all. But the interesting thing is differential phase contrast, because if you have a semiconductor device and you have a p-n junction and you position your beam to the single place, actually the electrical field will distort your transmitted beam by the electric field present. So on the detector, which is segmented, you will see a directional change. And if you have detector which is segmented at least by 2 4 segments, you can get information about the electric field, and then you can mathematically process the differential phase contrast either through integration or differential. And if we look at the images, so you can have images based on the directionality of the electrical field in the x and y direction, and then you can really have a differential phase contrast where you see the vector direction of the electrical field colored by the different direction. And it really, you can start to see that actually the structure of the contrast and of the electrical field represent the actual device. But if you look into theory, you can really look at the, what is the profile of the depletion layer, what is in the differential phase contrast distribution of the electrical field, but also you are able to basically localize the position of the p-n junction. And since it was already said today that the dopant control is critical for the device performance, this is interesting information to get at the end. And yeah, I hope that was all for me. I'm ready for question, and I guess I helped you to understand why electron microscopy is critical technology for semiconductor in general, but also for wide bandgap failure analysis applications.
Okay, so questions? No questions? Already answered.
You mentioned in the focus time, you mentioned the chemical effect
Uh-huh.
etching, but then you have only inert ions. Gas ions.
It's driven by
Where's
the yeah. So I didn't speak about the chemistry, but actually you inject the chemistry as a standalone chemistry, and then the interaction of the ion drives generation of secondary electrons, and these secondary electrons then help the molecule of the chemical precursor to decompose into the reactive state, and then this is how it etches chemically. So actually the chemical part of it is more important because this is what provides the etching. The ion you can imagine as the inductor of the mechanism. Yeah.
Mm-hmm. And so what are typically the chemical precursors here?
Yeah, so so there are, the thing is that it's called DX and DE. It has really marketing names. These are very complex precursor, and I think if you search internet, you will be able to find, even though it's IP protected, you will be able to find what type of molecule that is.
Thank
you.
Okay, other questions? Okay.
You said that there is a requirement of an hour already.
Yes.
But is there a similar requirement device?
So that's That's a good question. So I will maybe, okay, that will be a lot of going back. But if you look at this one, each of the stages has different requirements in place, right? So while here it's really about, you know, kind of like pushing the boundaries, using whatever type of analysis you can do in order to understand the things, the time becomes important over here. This is where you are looking into fast turnaround, because as you move on the curve up, basically any time you lose, you know, the company which is doing the devices is losing the profit, it's losing the revenue, because you lose the time, you know, of the manufacturing capacity of actual functioning devices. Now, if you move in here where you already have something which is called yield, you know, stabilized, actually there is still some aspect of the time, but what is most important is the reliability and the robustness, because if you are not able to find the defect, well, then you are not able to propagate it back and correct it, right? So this is how it is distributed. So here it's really about understanding the flexibility. Here at the intersection, it starts to become more repetitive, high volume, very much throughput based. So how much analysis you can get. And then at the end, really, I say always the defect is the king. So, you know, it doesn't matter if you do it fast when you don't understand the root cause of the defect.
Okay, any other questions before we close today's sessions? Okay,
Please.
As the process scaling, the device for feedback, actually, they become much smaller than before, right? So, what's the challenge?
For byte bandgap or for logic?
For logic.
Logic.
They are much smaller, right?
Yeah.
If you talk about the device size, they are 10 nanometers or even less than that. So
that's a good question, which has nothing to do with the topic. But the thing is that on the logic or memory, what you see is you have a change of the structure. So the structures are changing more dynamically than here. You have a change of the dimension, so it's getting smaller. But you have to imagine that each of these steps has a saturation level. Like you cannot, like, you know, for example, drive the dimensions to, you know, you cannot make, at some point you just cannot make it smaller, right? Because you will break boundaries and it will not work. And then the third one is you go 3D, right? So you start to stack it. While here it was all 2D devices, even logic was, you know, kind of, even though it was like, it is 3D structure, it's still a 2D device in one functional plane. You start to stack on top of each other. This is where memory is pivoting, you know, because we see transistor layers reaching 512 and maybe 1024 layers. And then I think the biggest disruption right now is that you take logic, memory, MEMS, whatever devices, and you integrate it within one package and within one chip. And now for that, the failure analysis is on completely different scale, because you have the whole device, which is now packaged. You have logic, memory, you know, whatever other types of chips inside. And then you start with the fact that you have something which is on nanometric scale, but you have also like in big volume, and you still want to have that resolution of being able to reach sub-nanometric scales, while, you know, having in the context of the device, which is, you know, a couple of millimeters wide. So this is, I think, the biggest challenge. And this is the difference between the wide bandgap and the logic memory.
Okay. Any other question? Maybe the last one? No? Okay, so Libor, thanks.
Yeah, thank you.
For that presentation. And okay, to conclude today's lectures, once again, thanks to all lecturers for their very interesting speech. And in several minutes, we'll be ready the dinner again in the room next to this lecture room. So all of you are invited to, let's say, continue with the discussions. And once again, those who are going for tomorrow's trip to Rožnov's site, if you are not familiar with Brno and Brno city, where to go at our faculty, just contact me and we will try to discuss how we are able to pick you up with the bus for tomorrow, or how you can move for some certain station, and then we will meet each other there. But there will be about, I think, 18, 19 people. So I suppose most of you know where to find our faculty. It's the Technická 10 Street. And those who are not familiar with this, just contact me after this session, and we will manage all the issues. So thank you very much once again for today's session, and see you tomorrow, maybe on Thursday, or if somebody of you will not join us, thanks for your participation, and see you in some next workshops. Thank you very much.